What's up, nerds? We are looking here at a inclines example where a man is unloading a heavy dresser from a moving truck. Before we start this example, I just want to talk for a moment about inclines in general and give you some tips for solving inclines problems. So we'll come back to our example in 1 minute, but let me show you in general how this problem will work and how you can set yourself up for success. So let's say we have a 40-degree incline here, which is similar to the problem we're about to do, and we have an object on the incline. Now, it doesn't matter how the object is interacting with the incline. It could be sliding down the incline. It could be at rest because it's being held by friction. Someone could be pushing it up the incline. It doesn't matter what is happening on the incline because gravity affects it the same way, no matter what's happening on the incline. So I just want to talk about the gravity portion of the incline for a moment. So here's the gravitational force, Fg. And no matter what's happening to this object on the incline in any inclines problem, we can do the same thing with Fg. Now, the difference between an object sitting on the ground and an object sitting on the incline is that the object sitting on the ground is fully supported by the ground. All of its mass, here, Fn, fully supports Fg. These are balanced. If it's on flat ground, Fn supports all of the gravitational force. Now, it's a little different when you're on a ramp because gravity will only support some of the gravitational force. Sorry, the normal force will only support some of the gravitational force. The ramp supports some of gravity, but not all of gravity. You can think that the steeper the ramp gets, the more vertical it gets, the less the ramp is supporting the gravity, the weight of the object. So, how do we determine how much of the weight of the object, the gravity of the object, is supported by the ramp? Well, the part that's supported by the ramp is perpendicular. So this is the perpendicular part. This upside down T symbol represents perpendicular. Fg perpendicular is supported and balanced by the normal force. This must be true because the normal force is also always perpendicular to the ramp. If you look here, this is 90 degrees to the angle of the ramp, and this is 90 degrees to the angle of the ramp. So these two forces must be balanced because the object doesn't fly away from the ramp and it doesn't punch through the ramp into the ground. It only slides up or down the ramp, right? It's only going to move this way or this way, right? It can accelerate up or down. Its velocity can be up or down, but it's not going to punch into the ramp or fly away from the ramp. So I'll do a little dash on both of these to signify these are equal. So to summarize, the part of gravity that is supported by the ramp is the part that is perpendicular to the ramp. Now, part of gravity also pulls the object down the ramp, wants to pull it down the ramp. Depending on the problem, it might not be successful in pulling the object down the ramp. Someone might be pushing it up the ramp, for example. But gravity in every inclined problem tries to pull the object down the ramp. Now, this part of gravity we call Fg parallel because it's parallel to the ramp. And this part of the gravitational force is trying to pull the object, to accelerate the object down the ramp. Now, I would recommend you start every inclines problem by finding what is Fg perpendicular and what is Fg parallel if you are able to find that information. Most inclines problems you will be able to find it, but not all. Now let's go ahead and find this angle here. So we know this is 40 over here, and we know this is 90 because gravity always points straight down. There's 180 degrees in a triangle. So this angle must be 180 minus 90 minus 40 equals 50 degrees. So here is 50 degrees. Now I also know, here I'll change colors to try and make this more clear, this to FG perpendicular is 90 there. So if this is 90 and that's 50, well, 90 minus 50 is 40. So we get the same angle as under the ramp. So for all inclines problems, the FG perpendicular makes the angle with FG that the ramp makes with the ground, right? FG perpendicular, let me highlight that for you. Let's find a new color. So FG perpendicular, wait, that's not the color I wanted. FG perpendicular and FG make the same angle as the ramp and the ground. Okay, so that's always the same. Now, we can do SOHCAHTOA on this triangle here, and sine theta is equal to opposite over hypotenuse. So sine 40 in this case is equal to FG parallel. So this 40 is opposite to FG parallel over the hypotenuse, which is FG. If I rearrange this, I get FG parallel equals FG sine 40, 40. That's equal to mg sine 40 because FG equals mg. Now we can do the same thing with the adjacent side, which is the perpendicular side. So SOHCAHTOA says cos 40 equals FG perpendicular. That's the adjacent side. So cos is adjacent over hypotenuse. FG perpendicular over FG. And if I rearrange this, I get FG perpendicular equals FG cos 40, which is equal to mg cos 40. Now obviously you'll have to replace the angle with whichever angle is appropriate in the problem, but this is an example of how you would find FG parallel and FG perpendicular in any inclines question. And these are going to be useful to you for solving any inclines question. Maybe not both of them in every question, but more often than not, you will need these to solve the problem. Okay, let's go back to our problem. A man is unloading a 28 kilogram dresser from a moving truck using a ramp angled at 39 degrees above horizontal. He is walking backwards down the ramp while holding the dresser, only letting it accelerate at 0.2 meters per second squared. So he's walking backwards and he's letting the dresser speed up a bit, but he's not letting it speed up a lot. He's letting it just gradually speed up a tiny bit as he backs down the ramp. So he's controlling the speed of the dresser. The coefficient of friction between the ramp and the dresser is 0.45. We are asked to find the force of friction on the dresser and the force the man applies up the ramp to support the dresser. Remember, he's pushing up the ramp to slow the acceleration of the dresser. He's not letting it accelerate too fast. So let's go ahead and draw the forces on the dresser before we get started with solving A and B. So we know that there will be a perpendicular normal force on the dresser that is perpendicular to the ramp. We know there is a gravitational force that points straight down to the center of the earth, towards the center of the earth. We know the man is holding the dresser so that it doesn't speed up too much. And lastly, we know that friction is also slowing down the dresser. It's acting opposite to the way the dresser is moving. So if the dresser is sliding down the ramp, then friction holds the dresser up the ramp. Now, as I said to you, for every inclines problem, I recommend you find FG perpendicular and FG parallel. And as we saw down here, that's equal to mg sine of the angle and mg cos of the angle. So let's go ahead and find those. So FG parallel equals mg sine of whatever angle we have. And in this case, FG parallel is equal to 28 kilograms. That's the mass of the dresser, times 9.8 times sine of 39, because the angle the ramp makes is 39. So once we put that in our calculator, we get 172 172.69. And then we're going to go ahead and find FG perpendicular, which is m times g times cosine of the angle, which is 28 times 9.8 times cosine of 39. And that is equal to 213.25. Now, I'm not rounding very much because I'm going to use these numbers in my future calculations. So I don't want to round and then do another calculation with a rounded number. You want to keep lots of decimals until you get to your final answer. Okay, now I'm ready to start my problem. So I look at A. A, what is the force of friction on the dresser? So I'm asked to find this, force of friction right here. And I know that the force of friction is equal to mu times Fn. That's the formula for friction. And sometimes you don't have all these values, and then you might have to do a F-net statement, a Newton's second law statement to solve the problem. But in this case, we do actually have this information. So we don't need to do an F-net statement to solve this problem. We can just use the basic friction formula. Now, Fn, as we discussed, is balanced by Fg perpendicular. The part of gravity pulling into the ramp is supported by the ramp. The part of gravity pulling down the ramp, which is here, Fg parallel, is not supported by the ramp. But the part that is perpendicular to the ramp is supported. So if Fg perpendicular is the same amount of force as Fn, I can write this as mu Fg perpendicular. Now I already found Fg perpendicular, it's right here. So I can just, sorry, this is part A. I can go ahead and multiply mu, which is given in the question as 0.45, times Fg perpendicular, which is 213.25, and I find that friction is equal to 96 newtons. Well, it's 95.96, and I'll keep that number aside in case I need to use it again. But to report our final answer, let's just round it to a nice 96 newtons. But if I have to use friction again in part B, I'm going to use this number in my calculation. So you use the unrounded numbers going forward. Part B asks, what is the force the man applies up the ramp to support the dresser? Now, there's no formula to calculate the force that the man pushes with. We just have to use the other forces and our knowledge of the acceleration to find the answer. Now, we know, because of Newton's second law, that F net equals ma. Another way of thinking of this is the winning forces minus the losing forces is equal to ma. The winners minus the losers will always get you the net force. So let's look at our diagram here. Because we're accelerating down the ramp, that means Fg parallel is the winning force, right? This force here, that's winning. It's the strongest force. It is the strongest unbalanced force. Now, the losing forces are any forces that are going against Fg parallel. And for us, that's these two forces here. Fa and Ff are trying to slow down the object, the dresser, from accelerating down the ramp. So those are our two losing forces. And Newton's law says that the winning force minus the two losing forces, so you can represent that like this. So winners minus losers being Fa and Ff equals ma. Or if you factor this negative into here, you can represent this like this. Winners minus losers, and you just make the losing forces negative. This is, you could skip straight to this step if you wanted to. So winners are positive, losers are negative is a valid representation. Now we are looking for Fa, so I'm going to go ahead and rearrange. I'm going to add Fa to this side plus Fa, or I'm adding Fa to both sides, and I'm going to subtract Ma from both sides, and I will get Fa equals Fg parallel minus Ff minus Ma. Now Fg parallel I already found. up here. Here's FG parallel, 172.69. And force of friction, I already found, is right here. It's 96 newtons, but I'm going to use the unrounded value over here for a more accurate answer. And let's go ahead and plug those numbers in. FA equals 172.69 minus friction, 95.96, minus MA, M is 28, A is 0.2, and I find FA equals 71.1 newtons. So the man, in order to slow down the box and not let it slide out of control down the ramp, is supporting it and walking backwards in a controlled manner by exerting 71.1 newtons on the box to control the speed of the dresser. All right.